now we're ready for the second part. And so, oh, well, I guess it's the second part. With respiration, we had like a particular set of steps that needed to happen in a particular order because we were using pre-existing molecules. With photosynthesis, it's more like the light dependent reactions are happening over here, and the light independent are happening over here at the same time, and the light dependent are just giving NADPH and ATP to the light independent, and it's just turning around doing its own thing. It's not like, you have to do one crank of this and then one crank of that. They're just kind of happening continuously right next to each other. So in the light independent reactions, this is where we're actually going to make sugar. So we're going to talk about making sugar. What we're not going to talk about is making energy. Up until now, every reaction we've talked about is in some way made energy. In this case, we are actually going to consume energy during the light independent reactions. And so the light independent reactions are also sometimes called the Calvin cycle. They also sometimes are called the dark reactions, which is kind of misleading because they don't really happen necessarily at night or something. They just don't need light. But they do need the products of the light dependent reactions. So this is a cycle. Calvin cycle, light independent, whatever, they're a cycle. And so just like the citric acid cycle, that means that we are making what we ended with in the previous set of steps. And so when we go through this whole thing, we're going to end with the same things we began with. My little stand's falling a little bit here. So we're going to draw like a circle kind of a thing. So when we do the first step, the light independent reactions, we're starting with what was left over from the previous cycle. And the thing that's left over from the previous cycle is a 5-carbon molecule. And this 5-carbon molecule is named OAA, oxaloacetate. Oxaloacetate is going to combine with a 1-carbon molecule of CO2. Whoop. So if you've got this 5-carbon OAA that's going to combine with a CO2, you're going to get a molecule that is how many carbons? That's right, 6. So this 6-carbon molecule, it looks kind of goofy. It actually is like this. There's like a branch. This 6-carbon molecule is going to exist for like that long. It's a very short-lived intermediate. And so we don't even give it like a name. This is just the 6-carbon intermediate. And almost as soon as we form it, it's going to fall apart. And it's going to turn into 2 molecules. And so those 2 molecules are going to be the same. So if you divide 6 into 2 evenly sized molecules, it will be 2 that are each 3 carbons long. And this molecule is called 3-PGA. And so it is 1, 2, 3 carbons long. It's called 3P because on carbon number 3, there is a phosphate group. 3PGA. And this molecule, 3PGA, has got one of them is going to have the carbon from this incoming CO2. And the other one, all 3 of them are this OAA. So this is a little different than in respiration. We don't necessarily need to keep track of which is the new, which is the old. Because in this case, this OAA that we're starting with is actually pretty energetic. It's not leftovers. It's leftovers from the previous cycle, but it's not like unuseful. It's still a pretty high energy molecule. And then we've got the incoming CO2. If anything, the CO2 is the least energetic of all of these carbons. So now we are now going to start to juice it up. We need to get this glucose molecule, this sugar, which means it needs to be this high energy, unstable molecule. So to get it to that state, we're going to start using up all these goodies that we've been saving. If you go back to the light dependent reactions, remember we made ATP. So we're going to use up a molecule of ATP. And we're going to use up that molecule of ATP to produce a DP, which means that one of the phosphate groups has been placed onto here. We're also going to use up our molecule of NADPH, which is going to donate a electron. And so when we get down here to this other step, we're going to have a 3-carbon sugar. And this 3-carbon sugar is named G3P. And so it's G3P because it's this. I think the G is, I can't remember the name of the sugar. I think it's glycerol. 3P meaning that on carbon number 3 there is still that phosphate group. So you might look at this and you're like, well, this one is called 3PG. It's got 3 carbons in a phosphate group. This one's called G3P, and it's got 3 carbons in a phosphate group. What's different about the two? They've all got a G, they've all got a 3, they all got a P. What have we accomplished between here and there? And the answer is that both of these are high energy sugars. It's not like it's a useless sugar. But when you get from this point to this point, by now we've added in those high energy electrons that came off that molecule of NADPH. We also added in a new high energy phosphate group, which came from this ATP. So although the structure is the same, the things that are actually inside there are not. So there's some high energy electrons that aren't accounted for in the way that we're showing these molecules that are in there. And there's also high energy phosphate groups, which are ready. And so this G3P, that's like a special molecule. That's a totally energetic, useful sugar. And we got 2 of them. So at this point, we can actually take those 2 G3P, smush them together, and we can make a 6-carbon glucose molecule. And we could do that if you wanted to. You could just take both of these guys and be done, and then you've got your glucose. But the problem is that this is a cycle, right? So we want to get back to this 5-carbon sugar. So if we just take both of those 3-carbon sugars away, we're never going to be able to recreate what we started with, and it won't be a cycle. So instead, one of these G3P is going to leave, okay? And that guy is going to combine with other carbohydrates to make glucose. Okay, so somewhere elsewhere in the chloroplast, it's going to find another G3P or some other sugar. They're going to combine together and make glucose or sucrose or some other sugar that might be needed by the cell. One of the G3P is going to stay. Okay, and it's going to stay behind so that we can get back to where we began. We can't just take everything and run, or we won't be able to do more than one cycle. So we need to go from 1 3-carbon G3P back to 1 5-carbon OAA. And you might say, okay, well, up here we added a CO2 on. That was 1 carbon. So why don't we just do that 2 more times? We'll put another carbon, bloop, and another carbon, bloop. But it's not as easy as that. The step right here where we add the CO2 on, that is with a enzyme which is named Rubisco. And Rubisco is very special. Rubisco is the other protein in this whole story about photosynthesis, which is going to define life on our planet, because it can take something that is inorganic, unalive, inert, CO2, and make it a part of a carbohydrate. And so that's a big deal to be able to take that CO2 in. And this is really the only time that everything's prepped to where we can do that. So we can't just add another carbon on there. So we want to be able to go from these 3-carbon sugars to a 5-carbon sugar, and we don't want any waste. And all we can do is work with 3-carbon sugars. So you can say, okay, well, we can get 2 of these 3-carbon sugars. But if we get 2 of the 3-carbon sugars, that's 6 carbons, we're going to have waste. We're going to have 1 left over. We can't make an OAA. All right, let's get 3 3-carbon sugars. Well, that's a total of 9 carbons. And so we could snap it in half, and we'd get 1 of these OAAs, but the other one's only going to have 4, and so it doesn't have enough. So if you just kind of think about what the math is going to look like, what's going to happen is that 5 of these G3P are going to get together and make 1 huge 15-carbon molecule. And it's just an intermediate. It's not going to hang around very long. But that 15-carbon intermediate is now going to break in 2 locations to produce 3 5-carbon OAAs. So just think about how this is 5, this is 3. We want to get to something that is divisible. The quickest way we can get there is with like 15. So we take 5 of the 3 carbons, we get 1 15-carbon intermediate. That's going to break into 3 5-carbon OAAs. And now we've remade what we began with, and so we can just kind of go through the whole cycle again. So during the light-independent reactions, you're going to start with OAA, which isn't really a reactant because it was already there, and CO2, and you're going to produce one, a 3-carbon sugar, which is G3P. You're going to remake what you began with, which is OAA. So this can actually be divided up into 3 parts. And this first part, where you're starting with your OAA, you're combining with the CO2, you get your intermediate, and then you get your 3-PGA. That is called fixation. Because in this step, you are fixing a carbon inside of this CO2. CO2 is not like a living, breathing molecule. And in this step, you're making it a part of something that is. So that's a big deal. So this is called fixation. You're fixing the carbon. The next part is called reduction. And that is because you are reducing the sugar that you made. You're adding electrons to it. And so during reduction, you add electrons, phosphate groups, and energy, basically, to this carbohydrate that you're kind of preparing to become glucose. By the time you get to this step, you've already fixed your carbon, you juiced up your sugar, and so it's been reduced, it's turned into this G3P. Now you're just concerned with getting back to where you began with. And so this third part is called regeneration. And during regeneration, you are trying to remake the molecule that you began with. So we've got fixation, reduction, regeneration. And those are the 3 parts of the light-independent reactions. This is all happening out in the stroma. And remember that the stroma is that empty space surrounding, where did I put my drawing? The stroma is that empty space, oh, here we go, that surrounds the thylakoid membrane. And so when this is your chloroplast, the stroma is this empty space around here. And so all of these enzymes are all kind of floating around inside of that empty space, and they're creating these G3Ps, which are then combining to form glucose or sucrose or whatever else it might be.